600 nanoseconds. Is it fast or is it slow? Alright, when was the last time you tried to guess performance of a piece of code and you were correct? Guessing performance rarely works out fine, so benchmarking is an essential skill in the toolset. Today we're going to look at how to do benchmarking in Haskell using Criterion library. Let's get started. What's up, everybody? My name is Artyom, and today I'm in the mood to do some micro benchmarking in Haskell. So, last time we worked on solving a particular coding interview problem, and we implemented two different solutions. One that uses immutable maps, and another one that uses mutable arrays and ST-monad. So today we are actually going to write benchmarks and see how the performance of these two solutions compare, which one is faster, which one is slower, and by how much. We also gonna implement like a solution for the same problem in Rust and benchmark it and see how Rust-based solutions compare to the Haskell ones. And an interesting twist is that since the last video was posted, Mr. Radu Grigore, who among other things proved that type checking in Java is undecidable. So he presented another solution which uses neither immutable maps nor mutable arrays and ST. So we are going to benchmark it as well and see how it performs. This is going to be very fun, so let's get started. All right, so this is a project from the previous video, but I already moved solutions to the coding interview problem from main module to swaps module. We need this so that we can define benchmarks. Now we use Cabal to build the project, and Cabal actually has support for benchmarking built in. So if we take a look at Cabal documentation, we should be able to find benchmarks somewhere here. Yep, exactly. Now, if we scroll down a little bit, we will see an example. So let's copy this and go back to the editor. Now, let's paste it. And we're gonna call actually this, oops, and this is gonna be bench. All right, so this is gonna be different as well. We're gonna call this bench.hs. And as for build dependencies, we are actually going to use a common stanza to move this sort of settings into like a common place. So here we are going to copy this and here we're going to remove this and remove from here as well. Now I don't remember how to include common, so let's go back to the documentation and see how to do it. Okay, so so basically we need to do something like this: import and then the name of the common stanza. Good. Going back to the editor, and here we import shared, and the same thing here. Okay, so this should be good now. We need to create this new file, bench.hs, and we need to define the main function. All right, so now we have everything set up and we should be able to build. So let's do this. So actually something isn't working. Yeah, so the dependencies are not seen. Let's see. Okay. Okay, good. So we actually need to set up Cabal version properly. Good. So here we have 2.4. Now let's try to build again. Okay, it works. Now that the basic setup is done, let's talk benchmarking. And for benchmarking, we're gonna use Criterion. So step number 1 is to add Criterion to the dependencies of our benchmark suite. So build depends, Criterion. Now let's go to the browser and see the documentation for Criterion. So here, luckily, they provide a link to the online tutorial. And in this online tutorial, there is like a sample that we are going to use. We're gonna need two things from here. First one is import, and the second one is main function stub. So let's copy this and go back to the editor. Now to bench.hs. Oops, wrong place. Then we're gonna need to import Criterion main. Then we save. Obviously we don't have fib function defined, so we need to remove this. All right. So now let's try to do this and see if everything builds. Yes, the benchmark was built, it was run, but we don't have any benchmarks defined, so nothing was run. All right, so before we proceed with benchmarking, let's just take a quick break and think what we want to do here. We have two different functions that we are going to benchmark. So it's minimum swaps and minimum swaps ST. And to benchmark these two functions, we need to define two different groups, one for map-based, another for ST-based solution. Then we also need to run the functions on inputs of different sizes. Let's say 10,000 and perhaps 10,000, something like this, or maybe actually 10,000, whatever. Anyhow, if we take a look at the signature of default main, we can see that it accepts a list of benchmarks, and B group defines a benchmark if you give it the name of the group and again the list of benchmarks. So the question is, how do we define a benchmark? And just one more thing here. As an input for our functions, we need to generate sort of random shuffles, and this generation shouldn't be part of the benchmark, it should be part of the setup. And again, we cannot generate random stuff without side effects, so environment setup should be an IO action. Now, if we go back to the browser and back to the Criterion page, let's see what functions we will need to create basically our benchmarks. Now, if we scroll down a little bit, we will find a function called perRunEnv. Now, we can see that this function returns something called benchmarkable. Okay, and as input, it accepts an IO action that produces the environment. In our case, it's gonna be like a random shuffle, and another function that uses this environment to kind of run the function that we'll need to benchmark. Benchmarkable is not exactly a benchmark. So let's scroll down a little bit more and see function called bench, which accepts the name of the benchmark, benchmarkable, and then it returns a benchmark. So these are the functions that we will need to use. If we go back to the editor, let's actually import Criterion. Oh my god. Good. From Criterion, we, as I said, will need functions per run env and bench. We also need another thing, like something that will allow us to generate these randomly shuffles. And luckily there is another package called random shuffle. Let's see. Okay, so this is actually exactly what we need here. So let's add random shuffle to the dependencies of our benchmark suite. Let's build it. Okay, cool. So now we restart LSP. And let's first define this function that will generate the input that we need. So let's call this function make input, and it will accept the size of the input. And what we're gonna do next is call this shuffle m function. Let's see. Yep. Now we see that this function accepts a list, and in our case it is a list from 1 to n. And actually we don't need a do here, so this is it. Okay, so let's just quickly check that the function we implemented works. So let's say random list of length 10. Okay, looks good to me. Fine. So now that we have this in place, we need to use per run env to generate the benchmarkable. Okay. Now, as we see here, first we need an IO action that produces our environment. So we need the length of the input, and the first argument is going to be make input n. Now, second thing is like a function that takes this list and then runs our supplied function. So here we have an input, and we also need the function that we're going to benchmark. And here we just use return f of input. Good. Now we have benchmarkable. And another thing is to take this benchmarkable and turn it into a benchmark. So there's a function called bench. It takes the name of the benchmark, and in our case just the length of the input should suffice, and then it needs a benchmarkable. Yes, and for this we're going to use make benchmarkable and f. Good. Now we need to be able to generate a group of benchmarks for a particular function. The input will be the function that we need to benchmark and the name of the group. And here we will have big group name. And then we need a list of benchmarks. And for this, we're going to do the following. So as I said, we need inputs of different sizes. 10, 100, and let's say 1000. And then we're just going to apply make benchmark to each element. Good. So now we have everything set up. So let's define the three groups that we need. So first one is gonna be for, and we need to import the swaps here. And the group name will be map, and the same thing for ST-based solution. Good. Now we have everything set up and hopefully it is going to work. Let's see. Interesting. So we have first data. Map-based solution takes about 2 microseconds for like an input of size 10. And then it scales more or less linearly with the size. What about ST? Is it gonna be faster? Yes, it is faster. So here we have about 560 nanoseconds for the input of size 10. And let's see, what about 100? So it is 500 nanoseconds for the input of size 10, maybe like closer to 600 nanoseconds. Is it a lot? Let's see, we have input of size 10, so it's about 56 nanoseconds for one element. I mean, this is obviously like super rough and not super scientific, but it should give us some idea of what is happening here. So it's 56 nanoseconds for one element, which gives roughly like 150 CPU cycles. So it seems a little bit excessive, right? So in order to see whether it is actually excessive or not, let's actually take a look at the Rust-based solution and see how it compares. Okay, so I will not go into details of how like this solution is implemented. It is very close to what we have in Haskell, like the same stuff, the same mappings from positions to elements and the other way around. And the benchmark is also defined using, surprisingly, a library named Criterion as well. But anyhow, so here we have 10, 100, and 1000. I guess we don't actually need this one. So let's save and let's run the benchmark. So it's gonna be cargo bench. Whew, let's see. All right, so now we have 85 nanoseconds for the input of size 10. Let's see if the trend is gonna be the same with the increase. So we have 439, so it's like 5x increase. And what about 1000? So it's 3 microsecond. All right, So what we have here is 85 nanoseconds per input of size 10. And if we divide by 10, we have like 8 nanoseconds per one element, which is roughly 15 cycles per element. Now this is actually closer to what one would expect. And what we see is that Haskell-based solution is about like 5-6 times slower, even though we use this advanced stuff like MArrays and ST and all this. Maybe there is actually some optimization opportunity here. So if we go back to the Haskell solution, okay, and we open the swaps.hs, let's think at ST. So what we have here is like these two functions that create arrays. And in this case, it is ST array. And inside ST arrays, we can see that it is mutable, boxed, non-strict arrays in the ST monad. So what we can do, what we can use instead is something called ST U array, where U stands for unboxed. So let's add ST U array to the import list. Okay. Yes, everything should compile just fine. And now let's run benchmark again. All right, so it's 539 instead of what we had, 564, not particularly faster. So we just benchmarked two different solutions, and we actually tried to optimize one of them a little bit with little success. And anyhow, although Haskell solutions work reasonably fast, it is not as fast as something that we can get in Rust. So the question is there a hope for Haskell to be as fast as Rust, or maybe faster? And luckily, we have another solution proposed by Mr. Radu Grigore. So let's take a look at his solution and benchmark it. So I haven't tried to benchmark it before. I don't know the results, if it's going to be faster or not. So I'm very excited with this. Let's head back to the browser. And all right, so this is the thread where the solution was proposed. Let's check the code. Copy, then get back to the editor. And I guess it would be easier just to create a new module for this. Let's call it swaps greek.hs, and then we paste this. Okay, let's rename this one to swaps Greek. Okay, now we need to add this module. Let's see if everything still builds. Module manual. All right, yeah, so okay, let's try again. Ooh, nice. All right, so let's go back and let's define another group here. I think we can actually just command this and just create a new group just for the Rudder solution. All right, so the moment of truth. Let's see. Oh. 1 microsecond. I mean, it's still better than map-based solution, but slower than ST-based one and MArray-based one. I wonder if we're missing anything here. Let's actually go back and, just for the sake of sanity checking, add another group, the ST-based one, and maybe also something like this. Not sure if it's gonna help or not. Let's see. All right, so ST-based one is still about 500-600 nanoseconds at input of size 10. All right, so sanity checking is done, and we still have 540 for ST and about 900 for just solution based on immutable arrays. And yeah, I mean, I actually expected something a little bit different, but still it was very exciting to see how these solutions actually performed. Now, that was a lot of fun. Well, at least for my definition of fun. But anyhow, to sum up, what we saw is how to set up benchmark suite for your project, how to use Criterion to run micro benchmarks, and also how to make sense of numbers. An interesting case here is that although Haskell is plenty fast, in this particular case, it is not as fast as Rust. Now, I'm obviously not trying to say that Haskell is inferior to Rust or anything like that. No. But still, it is an interesting case, and maybe it's actually a good idea to take a look at the generated assembly and see why Haskell solution is not as fast as the Rust one. Or maybe someone could actually just spot a mistake or suggest some other performance optimization. I don't have a very good experience optimizing Haskell, at least in this way. So any suggestions are very welcome. Anyhow, hope this was helpful. Thank you, and see you next time.